Structuring systems, an application of basic structural modeling. This is our review and conclusion in part 6 of this first series. We'll be concluding and summarizing the information in the conceptual design phase in this particular video. Again, this link right here gives you a link to my website where all the background information and slides are available. It's my Twitter account where I make announcements, and also there's send messages there. So the conceptual phase summary. What we're going through is the conceptual design phase, looking at the issues that would be associated with implementing Warfield's basic structural modeling concepts, and we approach that by developing some project objectives and goals, outlined the fundamental concepts and ideas, and we explored the general types of process applications. We picked a specific example of ordering cities, taking 19 unordered cities and ordering those, and we'll go through the process that we did with that in a summary fashion, and we'll talk about and we need to really design an inference operation, well, integrate an inference operation. The proof of concept for the integration mathematics, the inference operations mathematics was done by Warfield. The ordering of the data, that's part of the design goals in this particular activity. And then we really need to add another step to another component to structural modeling, which we call structural integration modeling, which provides a framework and methods for integrating the basic structural modeling and the interpretive structural modeling techniques. So our project goals and objectives were to demonstrate a basic structural modeling techniques, and these are mathematical techniques, so we needed a mathematics tool. So also wanted to identify an open source math product to support the activity. Selected the Sage math software from the University of Washington. And then to design a structural ordering process. That's one of the design goals of this activity, is to design one or more methods by which you can order the data within the system as it's presented in a mathematical or graphical form, and then implement an inference and empirical data approach. This basic approach integrates the collection of empirical data and also the inference based on the collected empirical data. So we need to design and think about the integration of the inference and empirical data approach, and then explore method phasing and transitions. What is the best way, the most efficient way to do this? Should we do randomly select 4, 5, or 6, or 10 objects, order those, and then do inference, or should we just select them 2 at a time and then do the inference on those once we order them? It's and that's part of the project that we'll explore in more detail once we have the software running and actually run a series of statistical experiments on the different approaches to solving a certain type of problem. And then, of course, communicate cost-effective integrated approach. What we want to do here is we really want to minimize the amount of empirical data, because collecting that costs money, and maximize the inference process and minimize the empirical data collection, because those, you have to expend resources for that. The fundamental concepts and ideas are essentially 3 types of truth. There's formal truth, there's common logic, factual truth is based on empirical data and the scientific method, and value truth, which is based on human and societal values and ethics, morals, basically what people believe are good, what's possible, those types of things. And systems engineering has to deal with all 3 types of truth. We create an approach that uses the same computational system. There's some disconnect between formal logic mathematics and factual and value mathematics. So we used the approach that was suggested by Warfield and expand that by using the SAGE tool and the abstract relation type, and demonstrate a computational approach with the open source tool. Of course, that's the SAGE tool from the University of Washington. And then we have the abstract relation type, which integrates the truth operations that was developed by the authors. And we have a marking space in the abstract relation type supports the formal and factual truth, and the value space in the abstract relation type, of course, supports the value truth. And then we talk about the concepts and the idea of a system structure, which also has components or objects and relations that are the basic parts of a system. So the three types of truth are formal truth, and these depend only on the logical forms and connectivities in the statements about the formal truth. Factual truth really depends on the state of the real world and how well a synthetic statement describes the real world. So what we're going to do here is actually have empirical data. We're going to collect data that's going to tell us whether or not something is true or false. And then the value truth is basically, it can be determined in a number of ways, and it can combine formal and factual truth, and is really the area where systems science and systems engineering and systems architecture really want to create value and increase value. So we need to use and understand and be aware of all these three types of truth, and develop tools and mechanisms that allows a facility to interchange and understand and compare these different types of truth. Some examples of these different types of truth and some things to note is, one, are they known by experience? Well, formal truth is not. Factual truth is, and value truth is sometimes yes, sometimes no. So we'll really base most of our operations on some amount of factual truth, some kind of scientific data. Process that scientific data with formal truth operations, and then compare that to value operations. And then the other concept to look at here is, are they certain? Of course, formal truth is certain, factual truth is not, and value truth is not. So in these operations, we'll be introducing some types of uncertainty will be associated with some of the formal operations that are integrated here. And the process is required to validate the inferences. So for formal, of course, a formal proof is necessary and sufficient. And then factual truth, observational data, and predictive success is what's important to validate. And value truth is many different kinds of arguments or many different types of systems or judgments or types of impacts can be used to validate value truth. So we'll take a look at these as we continue to go forward and develop the system and develop the code that's going to integrate it. And so the authors have developed the abstract relation type that's used to help integrate and deal with these types of truth and also the data that goes with these complex problem spaces. The abstract relation type has a marking space, an outcome space, and a value space. And this is kind of a general conceptual idea of abstract relation type. Here we show multiple value spaces. The marking space can also have multiple value. Well, the marking space can have multiple value matrix. The marking space can have multiple marking matrices. The outcome space can have multiple outcome matrices. Of course, here we show the value space with multiple value matrices. So there can be more than one matrix associated with each of these spaces, depending upon your problem type and how you need to organize it. The abstract relation type also has three sections. We just looked at the graphics section that has the matrices and the graphics representation. It has a prose description which is a formal pattern, and informal prose describes the mathematical and graphical relationship and also its application. And then with the mathematics and computer representation, of course, are the math equations and the computer codes that are used to generate the graphic representation and that are represented by the prose description. And these are model exchange isomorphisms, which were developed by Warfield, and you can change from any one of these representations of a system to another without loss of information. And it's an excellent way to communicate to a group that has different capabilities. Many people might understand a situation better if they're shown a graphic. Some people might understand it better if they're shown the mathematics. Other people would understand it better if they're shown the prose description. But even though people have facilities in one or more of these areas, the reinforcing representation of all three forms also helps. You can get the big picture with the graphics, you can dig into details, and once you get the big picture in the math, and you can also dig into details with a prose description. So the model exchange isomorphism using all three forms really allows you to communicate to a much wider audience, with an audience that has different capabilities, and also to communicate in more detail and more depth. And of course, we've defined a system as a relationship mapped over a set of objects. And we usually use the system's concepts in two modes. One is, of course, the design mode, and the other is the discovery mode. And most graphics and systems engineering approaches right now use their graphics, their prose, and their mathematics in the design mode. They're documenting a design, they're exploring a design, but basically mostly in the design mode. What we're doing here in this particular application is we're in the discovery mode. We're discovering the order of the relationships, and we really know the objects. We know the cities, we know what they are, but we don't know the specific relationships. So we're applying this set of system concepts in a discovery mode. So here's the system structure and its components. As we've defined a system as a relationship mapped over a set of objects. We know the cities, we know the objects, we know the general relationship is north of. We must discover the specific relationship between each city pair, and that then completely defines and structures the previously unstructured system. So the conceptual design objectives are objectives for this specific conceptual design activity are to create an automated ordering process, and we've looked at that and we've created some ideas, and we'll reduce those to code in the next set of activities. To create an integrated inference process, we've again discussed that and looked at the details, what needs to happen there, and create a process to identify the highest inference potential. Again, this is another area where we'll be optimizing the system once we have some operational code and we can run different types of test processes through it. And of course, our key design considerations are we want to maximize the use of inference and reduce the cost, minimize the use of empirical data to minimize the cost, and of course to minimize the cost of a structuring activity, and then to demonstrate the SageMath package application and how this can be used to support and demonstrate the mathematics of structure which were developed and published by Warfield. So the conceptual design phase, when we went through and looked at this, we've identified two basic general process steps. The first general process step is to initialize the process. It has two subcomponents, which is identify the cities and create the initial matrix. And then the second general step is basically loop until done, and that has 4 subcomponents to it. And in each case you obtain empirical data. How much? Do we do 5 randomly? Do we do 1 at a time? Do we do some number that's a fraction of the total known amount? So obtain empirical data, this will be something that we'll be looking at how to do that effectively in the future. Then you order the structural information. So this again is another design process, which is the ordering process. We infer additional information. Now this was mathematics for this was demonstrated by Warfield, and how to integrate that into our process again is another design consideration. And then of course go back to step 2.1. So you just keep looping through these until you've ordered all the systems. In this particular case, when we did these 19 cities, we did 5 steps, and that only took us 5 steps through to order all of the cities. And step 1, of course, we initialized the process. Then we collected empirical data on 5 cities, which were selected at random. We ordered the data, then we inferred additional information. And then step 3, we again selected 5 cities at random, collected the empirical data, ordered the empirical data, and we inferred the additional information. And then when we got to step 4, we started selecting empirical data on 1 city at a time, and this is where we would be looking at finding the highest inference potential for each city. But then we ordered the empirical data, and then we inferred additional information after we collected data on 5 cities, 1 city at a time. And then we again did that all over again. We collected more empirical data, one city at a time, ordered the empirical data, and we were done. So you can see it's once you start analyzing the process steps, they're fairly straightforward, simple set of steps that you need to apply recursively until they are complete. Now, this is our beginning configuration with our 19 cities. Of course, what we have here is like, this is city 4. Is city 4 north of city 2? Well, we don't know. We've got a 0 there with a yellow background. A 0 with a yellow background means it's unknown. A 0 with a red background means false. And logically we know, is city 2 north of city 2? Well, no, that's false. We're not going to allow that. And we don't have any empirical information about these cities, but we know logically that we will not allow a city to be north of itself. Is city 12 north of city 12? Well, no, we're not going to allow that for any of these. And of course those then are all represented by red zeros on the diagonal. Now here's our first set of randomly selected empirical data, and what we will do with this in the ordering process is we'll move all of the green ones that are in the upper triangular portion of the matrix into the lower triangular portion, and that will be our ordering process by which we do that. And this is the outcome of that ordering process. Now all of the green ones are in the lower triangular, the upper triangular has the red zeros. Then once we have the system ordered, then we apply the inference routine and we infer the new data points. Then we randomly select more empirical data for this particular process. We'll move all the green ones and all the blue ones, actually move all the ones into the lower triangular and order the process. And this is now all the cities ordered again to where all the ones are in the lower triangular. Then we infer, we do the inference process, add more blue ones, but everything's in the lower triangular now. And all the red zeros are in the upper triangular. And now we'll start collecting empirical data 1 city at a time at step 4. And then we will order that additional empirical data so that we have cities ordered again, and then we'll infer additional information. We have all these new blue ones here, and all the ones are in the lower triangular, which is the ordering goal. That's the design situation. And then we'll collect more empirical data, one city at a time, go through there, and they'll be working in the lower right hand corner of the matrix. And you can see then we'll order it again, we'll order the empirical data, and once that's done we have the inference, and we have all the cities ordered. We didn't really need to fill in all of the unknowns to get a complete order. That will also be another kind of area we'll need to research and investigate once we get the automated tool running. So the inference operation and application, we use the Sage Math operations for inference. We'll need to integrate that into a larger type of solution process. And we need to create unique Sage Math functions for the ordering and process, and also for the identification of the highest inference potential. We'll integrate the data input, ordering, and inference, so we'll need to think about what the human interface or the I/O or the user experience is on that, but that'll be later on into other activities. We'll design new process integration functions, and of course we create a system integration framework. That's the art, and also the structural integration modeling portions that we've added to this. And this is the structural integration modeling. So we're going to take and have structural modeling components. We have the basic structural modeling and the interpretive structural modeling. These were developed by Warfield. The authors are developing a structural integration modeling approach, which will allow us to integrate many different types of structural information into one format. And the system integration frameworks enable structural integration modeling and methods and techniques. That's the ART framework mostly that we have now, and we'll be using the Sage Math tool to explore and explain that in more detail. So that's the end of this particular series. This is part 6, the summary and conclusions of the conceptual design phase for this activity. That's the end of this particular video series. We'll have a new video series. I'll start around the 1st of January. I'll go back through and address each of these specific steps in a more detailed manner.